As Mr. Groff said, I'm Bryan Armstrong. I'm the application manager for Corel USA, which is headquartered in Mannheim, Pennsylvania, about a half-hour drive from here. We're an Italian-owned company that we manufacture electronic control solutions you guys may have seen in your HVAC lab. My role is to work directly with the equipment manufacturers in North America, Central America, and South America to implement our high-efficiency solutions into their products. And as Mr. Groff mentioned, I'm finalizing my bachelor degree through Penn State with energy and sustainability policy. Part of that was following a regulation, which I chose to pick HVAC specific topic of refrigerants that we use in our industry. So that's what the next hour or so, and I'm going to try to leave some time for some questions if you guys have any. But just for overall actually, what I want to mention is also I'd like to thank Ron Santini and Vera Cole for being my course advisor and the project coach. So just some housekeeping items. I know we all have cell phones, just please try to limit the use, just to try to get as much knowledge as you can out of this presentation. If you can put them on silent and not playing with them the whole time, that'd be great. Also limit any side conversations. I know there's some information maybe you want to talk with your counterpart beside you, just try to keep that quiet. There will be a Q&A at the end, and I did have to put the presentation already on a USB, so your instructor already has it. So thinking about the HVAC refrigeration sector today, we couldn't be where we are in 2017 without air conditioning refrigeration and the basic principle of taking heat from one place and putting it in another. Just thinking of refrigeration, the cold supply chain, if you will, taking food from harvest, transportation, storage, and then finally distribution in supermarkets or convenience stores. None of that would be possible without refrigeration. We wouldn't have the ability to eat bananas or coconuts or all the other great exotic fruits that don't grow here in Pennsylvania. And additionally, refrigerating medicines, so advancement in the medical industry, pharmaceuticals, and then also with the surgicals, type surgical suites where you need temperature and humidity regulation. So a lot of health saving, a lot of human health and health saving items are coming directly from the HVAC refrigeration world. Also commercial and residential air conditioning, so for your comfort cooling, and any process industry that may need a specific tolerance on temperature and humidity. If you think about the cell phones that I just told you not to look at for the next hour, we couldn't manufacture those cell phones without tight tolerances on temperature and humidity control in the manufacturing process, also in shipping, and then the telecommunication network. So all those Verizon and AT&T commercials, T-Mobile commercials, they have an entire network of cell towers. Every single cell tower has an air conditioner in it. Ironically enough, it's one of our controllers, and we have an expansion valve. There's a lot of other nice things that are in that, but it wouldn't be possible. So our human life as we know today is not possible without air conditioning and refrigeration. So don't think of your day-to-day is just a menial task. It actually means a significant amount for our society. If you look a little bit in the past as far as the history of how we move that heat from point A to point B, back in ancient times, they had ice and snow storage. So they would actually leave pots out overnight, and they would freeze. You would have a pit also that they could collect snow or water in. And then, when rivers froze over the winter, they would chop that up and ship it down south. They would also use like double wall insulation underneath the ground. So they'd use the thermal properties of the earth to be able to keep the ice cold. Additionally, evaporative cooling, so just the physical phenomena of like a waterfall and the mist evaporating off of your body. Evaporative cooling technologies were way back in ancient Egypt. They would build their cities around fountain structures that would funnel water from the Nile River to be able to evaporate in their city centers. Looking more recently, really you've seen the explosion from the invention of the vapor compression cycle. So I have a few dates up there. I'm not going to go through every one, but there's some notable scientists you may be familiar with. Michael Faraday in 1805 used ammonia to demonstrate artificial cooling. There was the first patent in 1835 for a refrigerator. 1842, excuse me, a doctor actually invented an air conditioning system to cool his yellow fever patients. And Albert Einstein even has a patent in 1930 for an environmentally friendly refrigerator, and it actually didn't use electricity or any moving parts. That had not been in wide-scale use and never will be probably, but it was something pretty interesting if you want to actually look at a patent. That's an interesting one. So types of refrigerants that are used in the vapor compression cycle. There's a lot out there. There's chlorofluorocarbons, or commonly known as CFCs. There's hydrofluorocarbons, the hydrofluorocarbons, and then the hydrofluoroolefins, and then natural hydrocarbons, ammonias, and CO2s. So I'm going to kind of touch on each one of these, different types of applications, different technical properties behind it, and then link it back to the environmental impacts of what these refrigerants and these chemicals are doing, specific for our sector and the entire Earth. Refrigerant manufacturers. So I just wanted to throw this slide up there to show you guys that there's a wide range of refrigerant manufacturers out there. You may be familiar with Honeywell and Chemours or DuPont, but there's several others. Arkema, Daikin is the world's largest equipment manufacturer in the air conditioning sector. They also make chemical refrigerants, as well as several smaller companies, RLX, SRF, several other smaller companies around the world that make chemical refrigerants. So is there such a thing as a perfect refrigerant? What are some of the things that we need to have to make a chemical a perfect refrigerant? The first one is a low evaporation temperature at atmospheric pressure. So you want to have good thermodynamic properties. The second would be very good heat transfer. The third would be not too high condensing pressure when you at nominal condensing conditions. Miscibility with the oil. I don't know, do you guys get into miscibility at all? Does anybody know what miscibility is?
Anthony?
No? So miscibility is the ability for the oil inside of the compressor to basically assimilate with the vapor refrigerant and be able to pass around the system to come back into the compressor. A compressor naturally will push some of the lubricating oil out of the compressor, and the miscibility level of that oil to assimilate with the refrigerant to be passed back around through the rest of the system. That's very important. You don't want to push refrigerant out and not be able to get it back. Push oil out and not be able to get it back. So no glide, no or very low glide. Does anybody know what glide is? This is going to be glide is going to be very important in your future career, because glide is the difference between the bubble and the dew point during a latent heat phase change. So in the entire time in the condenser or the evaporator, when you're going from a vapor to a liquid, usually that temperature remains constant. With a lot of these new refrigerants that are out there, that doesn't happen, that changes. So this is something very important for chemical refrigerant manufacturers, for component manufacturers, and equipment manufacturers to understand those technical properties. Another one is is limited drawbacks, so safety-wise, so no flammability and no toxicity. Low ozone depletion potential and low global warming potential. So these are kind of like the bullet points that we would love to be able to say, there's a perfect refrigerant that's going to hit every single one of these. But the reality of the matter is there's no such thing. So with an application that has certain requirements, you maybe be able to get a couple out of those, not all of them. Different applications may be able to get a different one, but there's never a magic bullet that's going to get all of them. So we in industry and you as service technicians going into your career, you need to understand the differences between all these requirements and which refrigerant is best for which application. It's good to know. So looking at kind of the history again of early refrigerant developments, from the early 1800s up to about the 1920s, all of those basic patent refrigerators that I talked about earlier were used with natural refrigerants. So something like ammonia, chloromethylene, propane, sulfur dioxide. So refrigerants that were very toxic and flammable. There were several cases of deaths and different illnesses from exposure to these types of chemicals. So a team of scientists at Frigidaire, actually led by Thomas Midgley, they worked on developing non-toxic and non-flammable refrigerants. And what the first one they dubbed was the diachlorofluorodifluoromethane. So I can't even pronounce that, and I've been making this presentation all week. I've been looking at that word, and I still can't pronounce it right. So what they did is they just said Freon. So that's how Freon was born, this very first word soup up there. That's Thomas Midgley. He went on to win two of the highest medals in chemistry. And he also was a serial inventor. He invented a lot of different things, and he ended up dying actually because he invented a machine to keep his body upright from polio, and it ended up strangling him. So if you're an inventor, just keep inventing, but try not to kill yourself. Another thing that was finally kept on developing with the CFCs was the next generation was the hydrochlorofluorocarbons. These are probably a little bit more familiar to you. And by the early 1970s, between the CFCs and HCFCs, worldwide production reached 1 million tons per year. And only since then it's been pretty much exponential until another point that we're going to touch on a little bit. So who's familiar with ASHRAE standards, or who's heard of any ASHRAE standards? Does everybody know what ASHRAE is? So ASHRAE stands for the American Society for Heating, Refrigeration, and Air Conditioning Engineers. So it's a group of air conditioning, refrigeration geeks that get together and they develop standards and they try to make this industry a more cohesive unit for developing equipment, for understanding design applications, for how to make a building work more efficiently. So one of the ASHRAE standards is ASHRAE Standard 34, which designates different safety classes and also assigns numbers to refrigerants. So you're familiar with these numbers more so than that big giant word that I'm not going to try to pronounce again. So essentially the numbering structure R, ironically enough, stands for refrigerants. It's pretty easy. But when you start looking at the individual numbers themselves, and I don't know how well everybody can see this in the back, but the pure refrigerants are 0, 1, 2, 6, 7, and 1,000. And that's the methane, ethane, propane, organic, inorganic, and unsaturated organic series. So those you may not see as much as the refrigerant blends. So refrigerant blends basically means you're taking the pure refrigerant and you're blending it with another pure refrigerant to get a refrigerant blend. And this is where you see the 400 and 500 series, which you're probably much more familiar with. So there's a breakdown between the 4 and 5 by zeotropes and azeotropes. It basically it's the chemical composition between the different types of refrigerant and the blends of those different types of refrigerants. So the zeotrope means basically that you have an equal composition between the two blended refrigerants. The other one, there's a non-equal. Pure components and isomers are what make up the capital letter at the very end. So you may have always wondered what that 134A lowercase, that means that there's an isomer. The capital is it's a pure component. So all of the refrigerants used in that blend are pure refrigerants. Whereas the 134A blend has an isomer molecule. On the other side of the ASHRAE Standard 34 is the safety classifications. So ASHRAE Standard 34 has been updated a lot fairly recently. And most recently, we've developed a new category of safety refrigerants. So primarily all those CFCs and HCFCs were in the A1 class, where there's no flammability, no toxicity. It's a great refrigerant. But now with more of these refrigerants that I'll get into later about low GWP and low ODP, we needed to add another class that has a higher flammability rating. So there's A2Ls. There's also an A2, and then there's finally an A3, which that's where your hydrofluorocarbons come in. So propanes, isobutanes, that kind of refrigerant. So the safety classification rating is toxicity by the letter, so A and B. No toxicity is A, higher toxicity is B, and then flammability. So the lower the number, the better it is. Higher flammability means a higher number. So all those CFCs, HCFCs, as I mentioned, are A1s. When we start to get into the new hydrocarbons, that's where you get into A3s. Ammonia is also a B2. So just for your reference, that's where ammonia stands. Does anybody know what ozone is? Ozone, exactly, so 3. So ozone is a molecule that was first discovered by this German scientist, Christian Friedrich Schonbein. It's essentially 3 oxygen atoms. Ozone in the atmosphere is necessary. We need to have ozone in our atmosphere to protect our Earth from harmful radiation from the sun. Ozone in like the troposphere, basically Earth up to like 31 miles, is considered smog or industrial pollution. So that's why you may hear in Los Angeles, you know, in the 90s and early 2000s, they had, you know, high ozone days or smog days. That's ozone is generated from industrial processes. So ozone is measured by 2 different ways that they put all this information together to collect models, and scientists are looking at the overall ozone layer on Earth. So they use ground-based and satellite-based measurements, and they express these measurements in Dobson units. The very first satellite that started measuring ozone was in the 1983, 1984 range. It was called the Nimbus 7 satellite. There's 3 satellites currently out there right now measuring ozone levels. In 1973, these two gentlemen actually published a paper. They calculated all the CFCs and HCFC molecules that were being released here on Earth's surface and what that would mean over decades of those molecules ending up in the stratosphere and the reaction that all those molecules would have with ozone. So essentially what happens is there's CFCs and HCFCs. One of the C's stands for chlorine, the other is carbon. So when chlorine is released and it gets up into the atmosphere and it reacts with ozone, it actually breaks down the ozone layer, which causes a big problem. So these two gentlemen released this paper, and they kind of really opened up the industry's mind, and we needed to come up with a way to start regulating the CFCs and HCFCs. Otherwise, it's going to continue to get worse, even if we would stop at that point in 1973. Because of all the molecules that were already released on Earth, it takes a while to get up into the atmosphere. They did go on to win the Nobel Peace Prize in 1995 as well for their work. So the way that ozone depletion works is you have your CFCs or your HCFCs or chlorinated gases that are released down here on Earth. They work their way up into the ozone layer, and then they react with radiation from the sun. It's a little bit hard to see in this picture, but what happens is a CFC molecule will go up and it will react with ozone. It breaks down the chlorine atom, and then essentially your chlorine atom interacts with ozone. You have a chemical reaction that creates oxygen, but then your chlorine atom cannot bond with that single oxygen atom, and it releases, creating a chain reaction. So basically one chlorine atom that goes up into the ozone can react with one ozone atom and create a chain reaction of thousands of ozone molecules being destroyed. And that's what was happening in our ozone layer right here. So this protective layer was starting to decay. We were killing off the ozone. So in time, when they were looking at all of those satellite-based imagery and also the ground-based imagery, you started to see, this is the bottom of the Earth. This is Antarctica. So this is the shape of Antarctica superimposed with the United States of America, just to show you the scale. So in September is the height of the ozone hole. So this was in 1981. This is in 2017. You can see, let's stop there. But you can see the size of the ozone hole here in 2017, which actually, due to a recent cold year, it was the smallest it's been since 1988. So it is showing signs of healing, but it's not until scientists project like 2070 until it's back to levels in 1970. So 100 years, and we stopped using CFCs and HCFCs only in the 90s. So significant impact that we had to the environment. An ozone hole typically is over on Antarctica, and the coldest location on Earth where the ozone depletion happens the best. That's where the best chemical reaction is in a cold environment. But after several weeks, it actually moves away and goes into areas of South America and potentially in some of the Pacific Islands. And it can cause serious problems with the high radiation from the UV rays of the sun, skin cancers, different eye injuries, immune system issues, and just overall imbalancing the ecosystem that may be in that place. So what we did as a global community is we got together in 1987, and several countries decided that they were going to rapidly phase down CFCs and HCFCs to start healing the ozone layer. So the Montreal Protocol, some of you may be familiar with, you may have heard that used before. That was, as I mentioned, in 1987, and it has now gone on to become the most successful treaty in human history with universal ratification of all 197 member nations. So it means every single country on the face of the Earth signed that treaty, and they have plans to phase down their chlorinated gases. This is a phase down schedule for HCFCs. It's probably hard to see where you're from, but 100% is the baseline that they used in 1989. They only started phasing down let me take a step back. There's a red line and a blue line. The blue line is basically developed nations, the United States, Europe, and the red line is developing nations. So developed nations, the United States, really only started phasing down their HCFCs in 2004. And there's a plan to go down to 0% of HCFCs by 2030. So you can see it's only been very recent that we started phasing down and putting in protocols that would implement this rapid phase down. 2007, the Montreal Protocol was updated to further increase this HCFC phase down. So the Clean Air Act. The Clean Air Act is a law signed by Congress that entered into force in 1970, and it's only been updated twice, in 1977 and 1990. The 1990 amendment actually incorporated all of the phase-down plans from the Montreal Protocol. So if we look at the Clean Air Act, the Clean Air Act is charged with decreasing these common pollutants. So starting at 0 right here, you can see that since it was enacted in 1970, they've done a very good job of decreasing by 69% those common pollutants, while our GDP, or gross domestic product, was over 200% in that time. Our population increased by 56%. Our CO2 emissions did go up by 27%, but you can also see the vehicle miles that we traveled as a country went up by 172%. So the Clean Air Act essentially is what the EPA, or the Environmental Protection Agency, that's the law of which they operate under. So within the Clean Air Act in 1990, there was an update to include what's called Section 612. You may be familiar with Section 608. That's where you get your EPA Universal Technician Certification, and they have the refrigerant management. But this is specific for what's called the Significant New Alternatives Policy, or SNAP. Has anybody ever heard of the SNAP program? There's some heads being nodded? Okay. So SNAP essentially requires the EPA to look at ozone-depleting substances and their possible substitutes for replacement in different applications. So SNAP creates a list for different industrial uses, such as air conditioning or refrigeration, blowing agents, different fire suppression, aerosols, sterilants, and adhesives. And they suggest that you use one substance over another in a specific application. The EPA SNAP has two types of ways that they regulate these different substances. The one is what's called proposed and then final rules, that they list or delist unacceptable refrigerants or chemicals, acceptable to use in certain conditions, and acceptable subject to narrow usage. And then they also release what's called notice of acceptability. So there's acceptable without any restrictions for a specific application. So just to give you an example of some of the rules that the SNAP program operating under the Clean Air Act published, and now are in what's called the Federal Register for all the regulations in America. The very first rule that they published was actually in 1995. So it took from a meeting in 1987 to entering into force in 1989, the whole way for America to actually put forth a regulation in 1995. So it's a difference of 7 years to actually start regulating these CFCs. That was Rule 1. Rule 14 in 2012 is basically saying that CO2 or R744 is acceptable alternative for vehicle air conditioning. Rule 17 is hydrocarbon refrigerants. Rule 20 and Rule 21 are probably the most controversial ones today. And basically what they did, and I'm going to talk a lot more about this later, is they said that basically the high global warming potential HCFCs now are going to be listed as unacceptable alternatives. And then they expanded it so July 2015 was the first Rule 20, and in December 2016 they updated that list with even more unacceptable refrigerants that have high global warming potential. So just technical information on the CFC R12, which probably I don't know if any of you guys will really run into it in your careers, but it's where we really started in refrigeration and air conditioning applications. It has an ozone depletion level of 1, which is very harmful, and a 10,680 global warming potential. It's banned or phased out completely in pretty much all UN nations. It was one of the most widely used refrigerant. But now, as I mentioned, it's completely phased down. R12 was mostly used in refrigeration and vehicle air conditioning, which was then replaced by R134. Another common HCFC would be R12. You guys will definitely run into this one in your careers, and there is a very rapid phase down of R22. So if you look at R22's ODP, it's only 0.05 with a 1700 GWP. But there's only 2 cooling seasons remaining in the United States until we get down to the 0 point of zero production. There's rapid reclaim and recovery plans. You guys should be getting into that kind of information from some of your EPA universal certification. But I think I read an article this morning that it was something like in 2016 there was 10 million pounds of reclaimed R22, and they actually think that that's on the low side. So they're looking at where all this missing refrigerant or it possibly is, or the EPA just completely messed up their numbers. But R22, you guys probably know better than I am. It's right now running at about a 25-pound cylinder is running about $600. So it's very expensive. And that's one of the strategies globally that they have, just increase the price and it's going to drive demand somewhere else. So the ozone hole today, I'd say talk about this a little bit earlier, but you can see there has been some recovery. This is measured in Dobson units. So here in 2017, we are higher than where we have been for the past decade and a half. And the size of the ozone hole area in millions of kilometers squared. Keep in mind Antarctica and the map of the United States. The ozone hole this year was 2.5 times larger than the US. But still, it's only up here compared to several of the other years in the past. It was much larger. There was just a report released last week that the ozone hole at 2 consecutive years has decreased in size. So it does show that there is global, the global regulations that we put for those chlorinated gas phase downs is working. So with the CFC and HCFC substitute, when they started being phased out, we had to come up with substitutes. And HFCs, hydrofluorocarbons, was the winner. These have very good technical properties. One of the problems with those is there's high global warming potential. So some of the common refrigerants that you guys all know and you interact with more than I do on a daily basis and will is R134A, 407C, 404A, 507A, and 410A. In various refrigeration, mobile transport applications, and residential air conditioning as well. So global warming potential, I've mentioned that a few times. Global warming potential, the value is equivalent to basically 1 unit of carbon dioxide emissions. So, or better known as R744 in the air conditioning refrigeration industry. So a GWP of 1 is R744. If you have 410A, it's 2,088. So that means for every 1 pound of R410A, it's the same as 2,000 pounds of CO2. So there's a significant difference between HCFCs and natural type refrigerants. So HFCs have grown significantly since we started that phase down plan on chlorinated gases. In 1990, it was almost 0. In 2010, you can see it's a significant increase. And it's estimated that by 2050, if you continue as business as usual, that 20% of all global greenhouse gases will be from HCFCs, these fluorinated gases. And in the United States alone, the levels at which we are today will be tripled by 2030. So less than 12 years, it's going to be tripled. In the US, if you look at the entire greenhouse gas portfolio, of course, carbon dioxide is the biggest one through electrical generation. Fluorinated gases, which is where HFCs fall in, it's only 3%, but it is the fastest growing greenhouse gas. Since 1990, it was at 0, and now we're way up here by over 270%. So it is a very formidable greenhouse gas, and we as a global community are working towards phasing that type of refrigerant down so we don't have this greenhouse gas problem with HFCs. So global warming, or the greenhouse gas effect, I know you've probably heard of this and you're familiar, but essentially on a normal, let me go back, on a normal Earth, the way that it operates is there's atmosphere and then you have greenhouse gas effect. So the greenhouse gas effect, it's important. We need to have a protective layer similar to the ozone of not having heat come into our Earth and then trapping there. Some of it does escape through the Earth's atmosphere. But what happens when you increase the amount of greenhouse gases is you increase the greenhouse gas effect, which basically means you trap more gases, increasing the amount of heat that does not get emitted into space. So you're heating up the Earth. The global average temperature has risen by almost 1 degree Celsius since they started taking measurements back in 1965 in an island in Hawaii. So with HCFC phase downs, because their impact with the overall global warming potential that they have, in 2016, there was a meeting of the parties to the Montreal Protocol. So it's the 28th time they got together since that meeting in 1987. And they met in Kigali, Rwanda. And they decided to start to phase down these HCFC refrigerants to avoid the potential global average temperature rise of a half a degree Celsius by the end of the century, which is most significant that we're going to be able to reduce with any global regulation or any country national regulation that we have on the table right now. So this is the phase down plan, and you probably can't see from where you're sitting, but essentially by 2040, 85% reduction of HFCs. The green line is the plan that Europe had, or what's called the EU, or European Union F-gas law, or fluorinated gas law, that started in 2006 and was updated in 2014. So that's the more aggressive line here. Then we have two red lines and then a blue line. Again, red is the developed nations, blue is your developing nations, but essentially 2040, 85% global reduction of HCFCs. So just some facts about the Kigali Amendment. The Kigali Amendment will what's called enter into force, so it will be a binding contract for these nations in January 1, 2019, if 20 nations ratify this, or 90 days after the 20th nation ratifies. Australia just last week was the 10th nation, and the European Union, which has 28 different countries, they have not ratified yet. This is still in their European Commission, and they haven't passed that law, or haven't passed that over. And the UK now, after they've exited the European Union, they started looking at this in their parliament. The 30th meeting of the Montreal Protocol convenes in 2 weeks, November 20th, in Montreal again, so it's the 30th year anniversary. And it's speculated inside of the HVACR industry that a representative from the Trump administration will go ahead and support the Kigali Agreement and America's participation. So looking at some of those global regulations that are out there, I mentioned the European Union F-gas laws. So in 2006, they passed the first fluorinated gas, or F-gas law, that basically broke down the entire sector by application type, and then refrigerant limits based on GWP, and a date that they would no longer be able to use those refrigerants above that threshold. So you can see there's household refrigerators and freezers, there's commercial refrigeration equipment, there's refrigeration and air conditioning equipment, so that would be like your supermarkets, that would be your convenience stores, and your air conditioners in commercial buildings. And then specific for centralized multi-pack refrigeration systems, so large compressor rack systems, transport equipment, so movable air conditioning, and then residential air conditioning as well. So you can see the dates are very aggressive. In the beginning of 2015, they already said that a GWP above 150 cannot be used on those applications. So domestic refrigerators and freezers primarily is 134A, which is way above that number. So in Europe, since that date and even before that, they've been using propane. I work for an Italian company. I've been over to some of their houses in Europe. It's propane in their refrigerator. It's about the same amount as some of you have in a Bic lighter. It's not that much propane. Looking at like the air conditioning equipment here, 750 by 2025. So that's significant from where we are today at R22 and R410A. Just kind of talked a little bit about this, but this is basically where these categories, so domestic refrigerators, refrigeration for commercial use, rack systems, and then movable air conditioner transport. So really you have some of the naturals, so you have your ammonia and your CO2, you have hydrocarbons, the isobutanes, the propanes, the other propane, you have some of the HFO blends, and then you have some of the HFC cut basically with HFOs, below 150 GWP. Looking at your split air conditioning systems, it expends it a little bit more, so you have all of these. That includes R32 as well as DR55. Moving on to more of the larger equipment and commercial applications, and also industrial, different types of applications, so data centers, chillers, those kinds of applications, would be up to 2,500. So basically you have everything except R22. So you still have your 410A, you have your 407A, you have 452A. You don't have 404 or 507A. So that's Europe. If we shift over to Japan, Japan has the Act on Rational Use and Proper Management of Fluorocarbons. So in 2014, they instituted a very similar law to the F-gas laws in Europe, but they only had 4 categories. So room air conditioning, commercial air conditioning, condensing unit, refrigeration units, and cold storage or warehouse. So very similar GWPs you'll see, 750, 750, 1500, and 100. Room air conditioning less than 750 beginning in January 1 of 2018 in Japan. 2020, 2025, and 2019 for some of these other applications. So looking at Japan, Japan actually does not have a specific fluorinated gas law. They just started in 2015 in HCFC, so back to the chlorinated gases. Their plan is to completely phase out all of these HCFCs by 2030. And in most cases, they're actually leapfrogging over the high HFC refrigerants for more environmentally friendly alternatives. So they follow the same models, just application specific. So you can see R22 is pretty much every application here, but their suggested substitute, propane, isobutane, CO2, ammonia, R32, and some HFO blends. So all very low GWP alternatives. Again, kind of jumping over what we've been using here is the high GWPs because of the CFC and HCFC replacements. Australia will, beginning in January, has a import limit. So they don't manufacture any refrigerants, they import all of their gases, and they have a limit on the amount of HCFCs that will be imported into the country with a decreasing cap every year. So it's aggressive phase down schedule, 85% reduction by 2036, which is 4 years faster than the entire Kigali Agreement and the rest of the globe is planning on phasing down. Canada, our friends of the north have a proposal. It's not an actual regulation, but they're trying to mirror what we do in SNAP as far as the refrigerants, but they're breaking it down by category and not just specific refrigerant substitute. So again, you'll see standalone medium temperature, low temperature, a centralized refrigeration system, condensing unit, chiller, mobile, with a little bit higher GWP than we saw previously in Japan and Europe's plan. But there is fairly aggressive dates by 2020, 2025 for all these different applications. Again, this is not an actual rule, it's just a proposal that they have in their government right now. So the United States, it's kind of small because it's probably the most complex regulation globally. There's a lot of things going on inside of the SNAP law. I mentioned Rule 20 and no, I didn't mention Notice 30. So Rule 20, man, I have to get really close to see that. So you can kind of see the bolded numbers here for the refrigerants that are being used in different categories. So you have supermarket, remote condensing, standalone equipment. So this is primarily your supermarkets and refrigeration, so food refrigeration. But 404A, you see 404A, there's 410, 134. So very common refrigerants that are specifically called out for not being acceptable for that specific application with dates. Same for Rule 21, which just extended that list for different applications. So chillers, centrifugal and positive displacement, as well as cold storage, warehouse, and household applications. So you see the difference between the US EPA SNAP is very specific on the refrigerant for that application, where the rest of the countries, especially in Europe and Japan, they just say for this application, just don't exceed this GWP threshold. So SNAP had a problem recently this year. Maybe you haven't heard of this, but there is an ongoing litigation between 2 chemical refrigerant manufacturers and the EPA. So in August of 2007, there was a federal district appeals court decision that told the EPA that they did not operate under the Clean Air Act, Section 612, that allowed them to regulate the ozone depleting substances when they extended it to the HFCs with a high global warming potential. And specifically, if you dig down into the details on the Federal Register of the wording that they used, the word replace was specifically used. So an application, take mobile air, or take residential air conditioning, specifically said replace and use this refrigerant, a substitute. So they were sued by Arkema and Mexichem, 2 refrigerant manufacturers, and the court sided with them. One of the judges said that, however, we might sympathize with the EPA's policy objectives. They may only act within the boundaries of the statutory authority given by the Clean Air Act. They exceeded that authority. And when the Obama administration in 2015 extended that SNAP program, it was ultimately meant to only regulate those ODS, or ozone depleting substances, and not extending it to non-ozone depleting substances. So in September 22nd, so exactly 45 days after the ruling, which was the limit for what you can submit an appeal for in the American court system, the chemical manufacturers Honeywell and Chemours, as well as the National Resource Defense Council, or NRDC, they submitted a full appeal. They submitted an appeal to the full 10-panel judge of the District of Columbia Circuit of Appeals Court that they asked to rehear the case. They have not yet said if they're going to hear it, and to my knowledge, there's not a deadline of when they have to determine if they're going to hear that case. If they decide not to rehear the case, the next step is to appeal to the Supreme Court. I had a phone interview with the government affairs manager from Arkema recently, and he told me that litigation can go on for at least 1 year, possibly more, on this, especially if the delay with the District of Columbia Circuit of Appeals Court, and then even if it goes to the Supreme Court, this case in the current American political landscape it's not that much interest. We have the tax, we have healthcare, we have a lot of other big issues that are getting more politicized viewpoint than our little industry and our refrigerants that are being used. So this could go on for a long time. However, I do want to reiterate that all the EPA rulings are still in effect until a court mandates the EPA to change their ruling. So everything that you know as far as Section 608 and what you have to do is, and Section 612, that's still in effect. And that will not change until the EPA is mandated. So there is some speculation on what could possibly happen. I don't think I have it on this slide, but what could happen as far as to give the EPA that ability to regulate non-ozone depleting substances is for an act of Congress, which will be needed if we ratify the Kigali Amendment. So when we ratify Kigali, it goes through Congress, it passes through Congress, and then Congress would have to amend the Clean Air Act. Another way that the EPA can start regulating these substances is through what's called the Toxic Substance Control Act. So it's just another act within the EPA's statutory authority. Actually, I did have it there. So that's exactly what I just said. One more thing I want to mention that kind of came out of this court case is we all know California is very, very eco-friendly. They're a little bit more advanced than the rest of the country. So their state has a Senate Bill 1383 that requires the state of California to reduce their HFC consumption by 40% by 2030. So California's equivalent of the EPA is called the California Air Resource Board, and the similarity between SNAP and California is what's called the short-lived climate pollutants. So that's the program in California that's looking at two things, and they just had a meeting on this 2 weeks ago. Number one would be the adoption of the EPA SNAP rules as they are, SNAP Rule 20 and 21, or I should say, an F-gas style, so European style limitation on GWP with compliance dates and then sales restrictions. So this was a chart of their proposal. 4 categories: stationary refrigerant with 50 pounds or more, stationary refrigerant with 20 to 50 pounds, air conditioning, and chillers. So you see the same target GWP of 150, 1500, 750, 150, but the dates are what blow my mind. It's 2021. That's only 3 years away. This is just a proposal, but it's much more aggressive than Kigali. And one of the big concerns that we have in the industry is by California setting this trend, there's what's kind of bypasses what's called federal preemption. So if you think about all of the business trades and everything that happen across state lines, now if you have a unit that's manufactured in California, they follow this law, they possibly will not manufacture in California anymore, they'll just move over to Arizona and start building their equipment there because they follow EPA. It's the same as all the marijuana laws that we have in the country. It's very similar. It gets into a lot of big gray areas. But this could also lead to other states having their own HFC regulations that then will cause a significant problem in our industry. So that's why we myself, I didn't mention this, but I'm a representative for our company on AHRI, so I do a lot of government advocacy. One of the biggest things we're promoting is federal preemption, and do not allow California to do this because it would cause significant problems for us in the industry. So looking in our crystal ball at what the future will hold when it comes to HFC substitutes. So there's a lot of things on everyone's mind, the entire spectrum of the industry. So how do we service this new type of refrigerants? What's the performance that the manufacturers are going to have to design to meet the DOE regulations? What's the leak management? Because now there's flammability and toxicity properties. Energy management as well. Some of these types of refrigerants are actually less efficient. Some of them are more efficient. Maintenance costs, the availability of not only the refrigerants but the components. So the compressor manufacturers, they have to design the compressors around the new thermodynamic properties of these refrigerants. Electronics manufacturers, we have to follow UL standards or underwriter laboratory standards for safeties on our relays. If they're in an environment where there possibly could be propane, even though that small refrigerator has the amount of a big lighter of propane, we still have to make sure that our relay is going to comply with a whole new set of standards. The availability of equipment and the trained workforce to be able to design, engineer, install, and service this equipment in the future. The operating costs for the building owner, different support from suppliers along the supply chain, safety. If you have a housewife that goes into a supermarket and she hears that it's using ammonia, or she hears it's using propane or flammable refrigerants, that may change her mindset of going into a certain store. So are these safe? The training for the service technicians that are going to be using this equipment, is it sustainable for the future, and how do we retrofit these types of applications that we have today instead of putting a whole new design engineered system in existing space? So some of the high GWP substitutes that we're looking at are natural and hydrocarbons. I've touched on everything so far. Propane, butane, isobutane, propene, ammonia, and CO2. You've probably you've heard of all of these. No ozone depletion potential, very, very low GWP. The problem comes with the flammability and the toxicity. So that's where you can see propane. It's A3. It's the highest flammability rating you can have in ASHRAE standard 34. Same with butane, isobutane, propene. Ammonia is a B2, so it's high toxicity and has a flammability property. It's also corrosive. However, we've been using that in industrial refrigeration for years. CO2, it's relatively low cost. However, it has a very high operating pressure. You're talking like hundreds and hundreds of pounds, possibly over thousands in some transcritical system. Also, there's some poor efficiency when you start to get into lower latitudes where there's a higher ambient, so more of the subtropical regions. So looking at specific replacements on refrigerants, for R22, there's plenty of already drop-in ready replacements. R34A, which is a Chemours product, maybe you've heard of it, MO99. R458, which is a replacement for both air conditioning and refrigeration. It's an A1. It's called with Gluon Energy. The product name is TDX. It's actually 15% more efficient than R22. Just by dropping that in, you can get a 15% energy efficiency increase. You may have also heard of R449, which is an HFO blend. That is an A1, but it also has a 7-degree Rankine or Fahrenheit glide. So the difference between the bubble and the dew during latent heat phase change is 7 degrees. So there's a design characteristic that we working with equipment manufacturers have to consider. Honeywell also has a 407F, as well as a 453A, which is another HFO from Comstar. Looking at 404A replacements, you can see there's 448A, there, which is another Honeywell. 452A, which could be used for both commercial refrigeration and transport, however, it does have a slight glide. There's, again, the 449A, and then the 407H, which is actually a Daikin chemical refrigerant that's being heavily promoted in Asia. 134 replacements. So some of the 134 replacement is, that number is completely wrong. So ignore that one. It's not that high. It's very low, actually. My apologies for that number. I don't know what it is off the top of my head, but it's very low. It's like less than 10. But 450A, replacing a medium temperature application, so heat pumps, chillers, and some refrigeration applications. 1234YF is a drop-in replacement for automobile air conditioning applications. That is an A2L. And then the R513A, another medium temp refrigeration application. A very good efficiency and no glide. So just talking a little bit about automotive. So there was what was called the MAC directive in the European Union to basically say that you need to move away from HCFCs in automobile applications. So globally, to date, there's over 50 million. I think I just read the number a couple weeks ago. It's somewhere in like the 70 to 80 million car range, or automobiles, I should say, not just cars. There's also service vehicles. And it's projected by the end of next year to be 85 million, but another article I read was over 100 million. There is a Honeywell plant that they just built down in Texas that's just specific for Chrysler, because Chrysler has switched over completely to 1234YF. 410A replacements, there's not a drop-in replacement, and 410A should be around for the next 5 to 10 years. When you start to get into the retrofits, then maybe there'll be a chemical manufacturer that's going to develop something, but for right now, there's nothing available in the market. So everything is a new design, specifically because of the A2L, the flammability issues, and also potential glide. So I mentioned 452B, which is an HFO and a low GWP. R32 you may have heard of, that's a Daikin refrigerant that they've been using for years in those split systems and VRF systems all over Asia. And then another one is the 447B, which does have a low GWP. It is just a little bit above that 1/700 threshold, but it's still a viable refrigerant for commercial air conditioning applications. All of these are A2L refrigerants, so they do have an issue with mild flammability. This is a chart that Emerson actually publishes, so it's kind of a crazy thing to look at, but on your y-axis you have pressures or your capacity. So you have your high pressure 410A, you have your medium pressure, so your 404, 407, and 22 and the like, and then you have your low pressure, so your 134A. And then you have GWP on the x-axis. So the boxes, A1 is the refrigerants that don't have any of the safety issues. The A2Ls is the flammability, and then the A3 is highly flammable. The orange is then your ammonia, basically, what you see on here. So what they're trying to say here is basically on a slanted line. So these kinds of refrigerants that weigh out here, high GWP, they need to move down in this range to try to get below some of these thresholds for different applications. So you see your 1500 threshold, you see your 750 threshold right here. So there's no really good replacement for 410A that's not in that flammability, or it doesn't go into a lower pressure in a complete system redesign. So that's Emerson's. If you just do a Google search, you'll find that pretty quickly. This is a Danfoss chart. So Danfoss displays it a little differently. They have GWP on the Y, and then they have your density or your pressures over here on the X. So high pressure 410A, and then down to low pressure. This is just other types of refrigerants. But then they actually show the line of flammability. So anything below this line has a flammability property. So you can see as you start to decrease your GWP, there's not a whole lot of options that you have that's not flammable. This is a screen grab from a Honeywell webinar. So they're showing their different products. Their N series is the non-flammable A1, and their L series is the mildly flammable. So different applications for replacing R134A. Here you have 515A. And then in the flammable side, you have your 1234ZE and your 1234YF. R22 replacements, they have 448A and 444B in stationary refrigeration. So 404 replacements, again, you have the 448A in commercial refrigeration. And then here in the 410A, there's nothing that Honeywell has available. It's not flammable. But if you look over on the flammable side, they have 452B for more commercial air conditioning applications, also probably for residential. And then there's a 447B for more of the industrial commercial applications for high pressure cooling applications. This is another screen grab from Chemours. So this is specific to their products. But again, you have 404A, they have 449, 452, and 454A. 134 replacements, so you're looking at 513, and then the HFO 1234YF. Here's the GWP as one. And then 410, the replacement 452B and 454B. So you can see some commonality between the component manufacturers, Emerson, Danfoss, the refrigerant manufacturers, Chemours, and Honeywell. There seems to be some common threads as far as what those replacements are going to be in the industry. So looking at I just picked a few applications. So residential applications. There's a report that one of the government-funded research laboratories published last year that said that 1.6 billion new residential air conditioners are expected to be added on to the electrical grid by 2050. And that's primarily because of the developing nations as they increase their GWP and they get more wealth. Air conditioning is really a luxury item. So they start to increase their amount of air conditioning applications in China and India, Malaysia, Brazil. So the very highly populated countries of the world are going to start to get air conditioners. They're going to put them into their electrical grid, and it's going to cause a lot of more problems with the indirect emissions from the air conditioning sector. Everything we've talked about so far has been direct emissions from venting refrigerant into the atmosphere. It's almost more detrimental when you add that many more air conditioners, if they're inefficient, what that's going to cause for the energy generation if you're still burning coal, or if you're still burning natural gas or the other types of fossil fuels and the carbon dioxide emissions that are going into the atmosphere. So one of the refrigerants here is for residential. Primarily in Asia, it's already switching over to R32. We probably will see that as a good mixture. Here in the U.S., we're expecting R32 and R452B, primarily for the air conditioning applications. But jumping ahead of myself. So R452B has already been tested in several Lennox products, some of the rooftop units. Medea has also selected this refrigerant for their mini splits in the US market. It's been tested on several different high pressure type chillers or positive displacement chillers. I know this graph is hard to see, and I can't really see it that well myself from there, but you have capacity, you have capacity, efficiency, and then the discharge temperature. So R452B is your orange, kind of orange, yeah. 410A is the comparison. So that's what this line at 100% is. So you can see the discharge temperature is much lower, the capacity is slightly lower, and the efficiency is actually higher. Compared to R32, which has a higher capacity, lower efficiency, and a much higher discharge temperature. And then another refrigerant, which is 447B, is about the same across the board. But we in the industry, we're kind of anticipating, as I mentioned, R32 and R452B, which has a 676 GWP, which is below that threshold for all residential applications. This refrigerant is a mixture, is a blend, excuse me, at 26% 1234YF, 67% R32, and 7% R25. So essentially, this refrigerant is the exact same as as 410A, except it adds this. So 410A was a mixture of these two refrigerants. We're adding this HFO, which has a much lower GWP, but has that flammability property. So that's why it's increasing up to that A2L. Both Honeywell and Chemours manufacture this refrigerant. So switching gears into a supermarket type application. So this is a chart that just shows kind of the complexity that you have with supermarkets. And if you think about a supermarket or commercial refrigeration application, it's the most refrigerant charge that you're going to have. You have a compressor rack system in the maintenance room, you have your condensers outside or on the roof, and then you have literally thousands of pounds of refrigerant charge through hundreds of braze connection underneath the concrete floor in a supermarket. Lots of leak potential, lots of refrigerant charge initially, and then the EPA allows you to vent something like 12 or 15% annually. So you can physically go back and put hundreds of pounds of refrigerant back in that system. So looking at kind of the future in the supermarket applications, there's a lot of factors that we have to weigh. So this chart has the type of system on the left, and on the top, it's the variables. So low GWP, refrigerant charge, leaks, complexity, technically the initial cost, maintenance cost, and efficiency. So looking at your traditional centralized system that I just described, you don't really have many low GWP options. The refrigerant charge is very high. You have a lot of leaks. It's not that complex. Initial cost is low, maintenance cost is low, and efficiency is very high. Some of the things that we're working towards is kind of a hybrid of a lot of different systems. So you have a distributed HFC system. So instead of using a centralized rack, you distribute all of that out into the space, whether that's plug-in type cases or like a water loop like you guys have here. The Hill Phoenix gave those cases to the lab. That's a water loop system where you have about 3 to 5 pounds of refrigerant charge per each individual refrigerant case. And there's also cascade or secondary type systems. Then you get into what's called a CO2 system or a booster system that can be what's called subcritical or transcritical CO2. Both of them have their technical complexities. But as you can see, low GWP, that's great. Refrigerant charge is great, but the complexity is very high. Another system that would be probably the best, the optimal system that we're trying to work towards, but goes with some of those flammability items that I'm talking about, is having a distributed propane system. So using propane as the primary refrigerant, and then there's a secondary system, whether that's water glycol, whether that's CO2 or ammonia or something like that. It splits up the system and allows you to have a lower GWP, lower leak rate, great. As far as complexity, it's not that complicated. Overall cost is pretty good. So these are kind of the factors that we're weighing out as engineers in the industry and understanding what's going to work for each application, and supermarkets are different depending on where you go in the globe. So looking at transcritical CO2 systems, in the United States we have almost 300 now. So there's 300 CO2 transcritical systems in the US. In Europe there's over almost 10,000 now. Japan is over 2,500. You can see some of these other countries are very small, but it's a growing trend here in the United States, CO2 stores. And one of the, it's really hard to see, one of the problems that we've had here in the US is we're a lot lower latitude towards the equator than you are in Europe. So a lot of these CO2 stores are working in an ambient environment that doesn't get like it is down in southern Florida or in Georgia, where you have a really high temperature, where CO2 just is not efficient. This is incredibly hard to see. But this bar right here is CO2 compared to 404, 410, and 134 in Illinois and in California, Southern California. So this is efficiency. You can see in Illinois, your efficiency is up here. In California, Southern California, it's way down here. So what's called technology called CO2 ejectors is becoming more prevalent in the industry. Corel has a CO2 ejector, Danfoss has a CO2 ejector. There's several other component manufacturers that are developing this technology to increase that acceptability of CO2 transcritical systems into farther southern latitudes towards the equator and hotter ambience. So you'll start to see more of this transcritical CO2 system with CO2 ejectors if you go into commercial refrigeration career path. Specific for the US, as I mentioned, there's that over 200 systems. So these are just a map of the different types of systems. So you have a transcritical CO2, which you're working with pressures up past 1,000 psi. You have secondary and you have cascade systems as well. So just kind of a map out of where all those stores are installed. So the industry itself has been working on preparing for HFC phase down. AHRI has a low GWP alternate refrigerant evaluation program. They're now in their third phase, where they're just get a bunch of funding money and they start testing all these types of refrigerants in every different type of application. So if you want to look at those 70+ test reports, they're available on their public website. If you go to ahrinet.org, you can see all those specific tests, you know, replacing R22, 134A, 404, 410, 407C. And they're working now on their third phase. They got a $6 million funding for further testing of these flammable refrigerants, some more hydrocarbon testing. One of the biggest hurdles that we have in the industry is compliance, especially America being the most litigious society in the world. Really, we have a lot of lawyers. We have a lot of safety protocols and different standards that we have to update. So I mentioned ASHRAE Standard 34. There's also EPA SNAP approval. So once we have those two components, we can move forward with different types of safety standards that we conform to, UL, EN, ISO, different standards that are going to take that specific application and that technology with that refrigerant that's now flammable, and they're going to have a group of engineers work for several years on updating that standard for a specific application in that building. Once it passes that safety standard, it moves on to national, state, and local building codes. Excuse me. So we can go through as an industry, and propane is a widely adopted refrigerant that can be used, and it can get down into some jurisdiction in BFE out of Alabama, and the fire marshal says you cannot use propane in this building. So that's how complicated this thing really is. And these code cycles operate every 3 years. So these codes are updated every 3 years. So you kind of have to catch it at the right time. Market preparedness, there's two types of strategies that really we have in the market. So the EPA SNAP has leveled heavy fines for the retailers. So this goes back a couple of years. Trader Joe's was fined $500,000, Safeway over $500,000, Costco 300,000 plus. There was actually an individual that he was stealing copper, but he was venting R22. He got 54 months in prison. There's a few other guys that I found in some research that they got over a year's prison time just for venting chlorinated gases. And when we get through this whole issue with the high GWP, I would expect to see something like that as well through the EPA. Another driver that you have is cost. I mentioned earlier that if you can put a price on carbon, which is a big political debate now, but in Europe that's what they're doing. They're looking, the suppliers are looking at the actual equivalent of CO2 emissions, and they're increasing the cost per ton of CO2 emissions. So you'll continue to see refrigerant prices rise as we get closer to those dates internationally. So coming to my end, and as part of my policy evaluation, I needed to give a personal opinion on the specific court case. So this does not reflect the industry. It does not reflect Corel. It's just my personal opinion on this case. It's a lot of words, but essentially, we're prepared as an industry, I feel, to take this on technically from an efficiency standpoint, and also from the chemical refrigerant standpoint that we're using in our products. Regulatory certainty is needed. You can't have one regulatory agency say one thing and another say another, and then a state level regulatory agency say one thing that doesn't jive with the EPA. So we need a clear path for our industry to understand where we're going as far as being more environmentally friendly with our equipment. I truly believe that Arkema and Mexichem, the chemical refrigerant manufacturers, were correct. And while they, from a business standpoint, they're losing ground to Honeywell's and Chemours. If you really boil it down, that's what's happening. They don't have those replacement refrigerants. If you're paying attention when I was mentioning all those different alternate refrigerants, those two were not mentioned. But from a legality standpoint, the court ruling does show that the SNAP program is flawed and it has not been updated to reflect high GWP refrigerants. And the EPA should adopt more of a clear market-driven approach. So looking at not just a specific refrigerant for a application and saying if it's acceptable or unacceptable, saying this is the application and you cannot cross this GWP threshold, which is the same as every other program in the globe, really. So I also feel like the United States of America needs to ratify the Kigali Amendment, which will most likely happen, we're speculating. And that the Congress needs to either change the Clean Air Act to allow the EPA to regulate the high GWP, or the EPA needs to look into the Toxic Controlled Substance Act. So with that, I'll adjourn, and I have 7 o'clock, so that's just about an hour. I'll gladly answer any questions that you guys may have.
Yes, how was from different agencies, how was the GDP, not GDP, the GWP, how was that, like how did they determine that?
Yeah, so the GWP, or global warming potential, is actually calculated from what's called the IPCC. It's an intergovernmental panel on climate change. So there's some like 300 different scientific entities that get together from over like 100 different countries every year, and they work on different chapters that they publish. And I think it's every 4 or 5 years they release a new assessment report. So you'll see AR4 is the 4th assessment report. The latest one is AR5 that they're working on. So they're going to update those GWP levels. But they look at a lot of chemical properties for how long that refrigerant is going to stay in the atmosphere, and also the radiative effect of how much it's going to actually warm the Earth.
Thank you.
Yep.
Bryan, you mentioned CO2 ejectors for transcritical.
Right.
How do they work?
It's a great question. I'm not the right person to ask that question, but basically what happens is it is a CO2 ejector inside of a CO2 system, which CO2 is a unique refrigerant that has what's called a triple point. It's not vapor, it's not liquid, it's not solid, it's some other weird type of issue. But so it's not a traditional vapor compression cycle. You have what's called a subcooler instead of a condenser. And the CO2 ejector essentially uses a booster to have the CO2 that's going through the system hit like supersonic speed, if you will. It basically just pushes the refrigerant around the system. I can get you some more information because that was a horrible explanation. Any more questions?
All right, Bryan.
Silence is usually acceptance. But this is you guys are going to see this. I mean, it is going to come into the industry in less than 5 years. You're going to start to see a lot of different refrigerants out there.
Thank you.
Thank you, sir. So where are you guys going as far as the career path?